In this video, we'll take a look at the concepts of velocity and acceleration and how they're related using derivatives, and also what a second derivative is. And we're going to start with a few examples on this page and some following ones as well. This is a displacement function. I haven't got units on here, but S of t represents displacement. It could be in meters, for example, or feet. And this is t represents time on this axis, perhaps in seconds. It doesn't really matter what the units are. And we're asked to answer several questions about this displacement time graph. Now, since this is displacement, the slope of the tangent line at any point gives the rate of change of displacement, and that will be the velocity. So, for example, if at time 0 I want to know what the velocity is, I would draw a tangent line in at 0 and estimate its slope. And so this goes, if we start right here at 0, 0, we go over 1 unit, we go up about 5. So that tangent line has a slope of about 5. So at the time of 0, the velocity would be about 5 units per time, whatever the units are. Now in B it says, when is the velocity faster at A or B? So we would estimate or draw in the tangent lines at A and B. So there's one at A, and there's another one at B. And notice the one that went through A is steeper. So that means that at A, the velocity is faster because there's a steeper tangent line. Next, we're asked, what's the velocity at C? Well, at C, that's a maximum point. So if we draw the tangent line and it's completely horizontal, so that has a slope of 0, which means that the object is stopped. The velocity at C is 0 because there's a horizontal tangent line which has a slope of 0. Next, what happens from D to E? From D to E, the displacement is constant at 4. So from 4 to 5 to 6 up to 7, so from 4 to 7, whatever the units of time are, the displacement stays the same. So if something's displacement is staying the same, then it's stopped, it's not moving. What happens at F? At F, notice we have a minimum point, so it's the same idea as at C here. If we were to draw in the tangent line at F, it would also have a horizontal, which is a horizontal tangent line, which the slope is 0. So the velocity would be 0 at F. Flipping over to the next page, on this page we have a velocity time graph. So this is a graph of the velocity. And if we want to find acceleration, acceleration is the rate that velocity changes. So slopes of tangents here will give the acceleration. So at A we're asked, what's the acceleration at time 0? So at this point we would draw a tangent line. And so notice if we go from 0, 0, we go over about 7 and up 1. So it's actually a fairly shallow tangent line. It's not very steep at all. So the acceleration is around 1/7, which is fairly small. When is the acceleration faster at A or B? So we would draw tangent lines in at A and at B. And so notice that the one through A is very slightly steeper. Their accelerations would be quite close, but because A's tangent line is a little bit steeper, then we could say the acceleration is slightly higher at A than at B. What's the acceleration at C? Well, this is a local maximum point, so if we draw in a tangent line there, it has a slope of 0, so at C the acceleration would be 0. What's happening from D to E? So notice from D to E, the graph is completely horizontal, so the velocity is staying constant at whatever this number is. So if there's a constant velocity, acceleration would be 0. Constant velocity means the velocity is staying the same, which means there would be no acceleration. Last question on this page, what happens at F? So if we were to draw a tangent line at F, it would not be quite horizontal, it would be sloping down like this a little bit. So we would say that the object is slowing down. Perhaps it's going to be stopped soon, but we wouldn't know that for sure. All we could say is that it's slowing down. Slowing down, if we draw the tangent line in, notice it has it's not very steep, but the tangent line would have a negative slope, so that's why the acceleration is negative, it's slowing down. Now, so if S of t represents a displacement function, then velocity is defined to be the rate that displacement changed, the derivative of s of t, and acceleration is the rate that velocity changes. So a is v prime, or v prime would be the same as s double prime. The double prime means that we have differentiated displacement twice to get acceleration. So differentiate displacement once to get velocity, differentiate it again to get acceleration. In this example, we're asked to find the velocity and acceleration functions for each of these displacement functions. So we're using power rule here to differentiate this. So the derivative of 2t cubed, remember bring the 3 down, 3 times 2 is 6, and decrease the exponent by 1. So the derivative of 2t cubed would be 6t squared. The derivative of 36t would be just 36. Remember, there's really an exponent of 1 here. When you bring 1 down and multiply by 36, that's 36. And then if the exponent was 1 and you reduce it by 1, that would give an exponent of 0. Remember, t to the 0 is the same as 1, so we don't bother write t to the 0 or 1 here. 36 times 1 is just 36. The negative 10 is a constant, so its derivative is 0. So that's the whole velocity function. To differentiate that again, we would then get the acceleration function. The derivative of 6t squared would be 12t. 2 times 6 is 12. Decrease the exponent from 2 to 1. And again, 36 is a constant, so its derivative would be 0. So that's the acceleration function. Now in B, notice that the 2t will divide evenly into each of those expressions. So we should do that first, and then we'll differentiate to find the velocity and acceleration functions. 6t to the 5th divided by 2t would be 3t to the 4th. Negative 24t to the 4th divided by 2t. Negative 24 divided by 2 is negative 12. T to the 4th divided by t is t cubed. And then dividing the 2t into the 18t cubed is 9t squared. So we would differentiate this to get the velocity function. The derivative of 3t to the 4th is 12t cubed. Derivative of negative 12t cubed. 3 times negative 12 is negative 36. Subtract 1 from the exponent. And the derivative of 9t squared. 2 times 9 is 18. T squared reduces by 1 to give t to the first. That's the velocity function. The acceleration function, derivative of 12t cubed, would be 36t squared. Derivative of negative 36t squared would be negative 72t. And the derivative of 18t would be just 18. So that's the acceleration function, which is the second derivative of the displacement function. Flipping over to the next page, in this example, and it's continued on the next page as well, an object is launched vertically from the ground. And we're told that its height is measured in meters at time s. The time is measured in seconds. So t represents the time in second. H is the height in meters. So we're asked, what's the object's initial velocity? So this is displacement, or height. And so we would differentiate to get the velocity function. So the derivative of 40t would be 40. The derivative of negative 4.9t squared, the 2 comes down and multiplies by the negative 4.9 to give negative 9.8 t to the first. Now initial means at time 0, at the beginning. So we would put 0 in place of t. So h prime of 0 would be 40 minus 9.8 times 0. Now this would be 0, so h prime is just 40 meters per second. That's the initial velocity. That's the velocity with which the object was launched. In B, it asks, when does the object reach its maximum height and how high is it at that time? Now let's say the bottom of the page here is the ground, where it's launched from. It rises to some point, and then it gets to a highest point, and then it starts to fall. Let's define up to be positive. So positive velocity here, and then when it reaches its highest point, its velocity is actually 0, and then it starts to fall, and the velocity becomes a larger and larger negative number. When it's at its maximum point, again, the velocity is 0 because it goes from a positive velocity to a negative velocity, so it has to pass through 0. So to find when the maximum height occurs, we would set the velocity function to 0. So we set our velocity function to 0 and solve for time. So rearranging for t, 9.8t would equal 40, and then divide out the 9.8 and get t is 40 over 9.8, which is about 4.08 seconds. So that's the when part, and then how high is it at that time? So we really want to know how high is it at 4.08 seconds. Well, this is the height function or displacement function. So we'll put 4.08 in place of time. And that's the calculation. So that works out to about 81.6 meters. So then we would say that it reaches its maximum height of 81.6 meters at 4.08 seconds. Continuing on the next page, we're asked to see what is the object's acceleration at 2 seconds. Well, we would have to go back to the velocity function and differentiate this. Now, the 40 is a constant, so its derivative would be 0. The derivative of negative 9.8t would just be negative 9.8. So that's the acceleration function, negative 9.8 meters per second squared. Now, notice that it's constant, and this is the actual acceleration near the surface of the Earth. So it really doesn't matter whether we're asked to find the acceleration at 2 seconds or any particular time. A of 2 would be negative 9.8 meters per second squared. A of any time would be negative 9.8 meters per second squared, because that's the acceleration of any object falling near the surface of the Earth. D, when does the object hit the ground, and at what velocity does this occur? Well, it took, and I forgot my statement up here. At 2 seconds, the object accelerates at 9.8 meters per second squared down. So, it took 4.08 seconds to rise to its highest point, and so it would take the same amount of time to fall. So, 4.08 seconds up, 4.08 seconds down. So, a total of 8.16 seconds occurs between when it's launched to the highest point and then back down to the ground again. So that's the when part. Now, at what velocity? So we will go to our velocity function and fill in 8.16 seconds. So h prime of 8.16 works out to be negative 40. And so this is an interesting thing here. Remember from the previous page, it was launched at 40 meters per second up. Notice that when it hits the ground, it's traveling at the same speed, but of course down, okay, because it's falling. The negative just means, of course, it's down. Now, last page here, there's actually 3 graphs here. This is a displacement function, y equals s of t. S of t represents displacement. The derivative of displacement is velocity, so this is a velocity function. And then the second derivative of displacement, s double prime, would be acceleration. So this acceleration is also the derivative of velocity. And I've taken this graph and the velocity one and enlarged them a bit, and I'll talk about the acceleration a little bit, but I want to make some connections between these different derivatives. In displacement here, notice that all the way along here, the slope would, if I drew tangent lines, any tangent lines here would have a positive slope. And remember, the rate of change of displacement is velocity. So positive slopes all the way along here. And so that's why in this graph, in the velocity value is positive all the way along here. Remember, this is the velocity time graph. I'm not talking about tangents here, just the actual velocity. For example, the velocity there is about 18. The velocity there is 20. The velocity there is 10. What the actual y values would be. Okay, so positive slope here, so the velocity values are positive. At this point, if I drew in the tangent line, it would be horizontal, which means that the velocity should be 0 there, so that's why the actual y coordinate would be 0 here. Okay, notice that's right at 2.5 seconds. Okay, I'm translating straight down from one graph to the other. Negative slope all the way along here. If the slope is negative for the displacement function, then that means that velocity is negative all the way along here. So that's why in the velocity graph, the y values are all negative here between this point and then this point again. This is another point where the tangent line would be horizontal. It doesn't matter that it touches the t-axis, just that the tangent line is horizontal there. So if the tangent line is horizontal for a displacement function, that means the rate that displacement is changing is 0. So that's why the velocity is 0 there. And then we're back to a positive slope again. and in which case for the velocity it's a positive velocity again. So that's some of the connections between displacement functions and velocity functions. Now if we go back to this graph here, positive slope all the way, negative slope all the way along here. Any tangent lines that are drawn here. And so notice at this point right here, if we translate right down the acceleration function, the acceleration is 0 here because the tangent line right there would be completely horizontal. Okay, so negative slopes all the way along here. That's why acceleration is negative here. And then it changes, so that's actually slowing down. That's why the acceleration is negative. And so it goes from slowing down to speeding up. Positive tangent lines here. Remember, this is the velocity function, so the slope of the tangent line is the acceleration. So positive tangent lines all the way along here. That's why acceleration is positive. This point is about 3.7. I'm just noting here. So a negative acceleration below 3.7 and a positive acceleration greater than 3.7, which would be right along here. And that's because the slopes of the tangent lines here are positive. So that's some of the connections between displacement, velocity, and acceleration, or a function, its first derivative, and its second derivative. And that's the end of the lesson.